Okay, how's everybody today? Doing good, doing good. Okay. We're a couple days out from the end of the fifth, sixth week. So remember tomorrow morning, if you have any outstanding assignments to turn in, of course, within the 10-day time frame, if you have a retake that you can still take care of, anything like that, come on in. I'll probably open up a little early in the morning because it is the last day. But if you need any help, let me know. I really think that's all I got. The only other item would be next week. Tuesday and Thursday, we're taking the English 1 and English 2 STAR exams. So if you are already completely done with that, it does not affect you. You'll be coming in at 1:35. That's when the tardy bell will ring. Tuesday will be periods 1 through 4, so I will not see you on Tuesday, but Thursday will be 5 through 8, so I will see you then. That'll be about 30 minutes each, so we will be able to keep moving. Hopefully, by the end of next week, I'm hoping to be done with the majority of our calculus unit. So we'll kind of see how that plays out. And I am going to go ahead and get you the first review packet on Friday, so you can go ahead and start looking at it. Speaking of, has anybody taken just a few moments to look over the released paper exam I gave you, the mark scheme? Okay, so many hands going up. That's what I like to see. All right, but if you have not had the opportunity, please go ahead and take a look at that at some point. Like I said, one problem. Okay. All right. Well, oh yeah. Excuse me. So we've been talking about limits, and we've been talking about some of the algebra concepts that go along with these different functions, but mostly we've been using these tables here to go ahead and help us figure out what the limit is going to be. We saw our first one yesterday. The limit does not exist, where as we approach the value of x from both sides, the corresponding y value in the function, it does not approach the same one. Okay, so let's see. I believe we're on example 6. So find the limit as x goes to 0 of 1 over x squared. Now, I can also go ahead and plug this in the calculator if you want, and I can talk about why this is, but I went ahead and sketched a graph of it right here. Now, what's the one value of x that we will absolutely have trouble with? Okay, 0. Now, you'll notice that's why I have an asymptote here. It's because the function is undefined. So at 0, there is some kind of issue. But just because, we've seen the function is undefined at a specific value of x doesn't necessarily mean that the limit doesn't exist. Okay, so let's go ahead and go to the table here. So 0 is the domain element in question. We're approaching it from the left, so this would be the limit as x approaches 0 from the left. Okay, the limit as x approaches 0 from the right. And again, this isn't really necessary for IB, but I just wanted to go ahead and make sure that you understand the limit itself. What we're trying to find only exists if you're approaching from both directions and you get the same value. Okay, so why don't we go ahead and just start plugging in some values and see what happens, starting with negative 0.1. So I'm going to go ahead, if I can pull this up. So control divide, I'm going to say 1 over, whoop, did not let me do that. There we go. So 1 over, parentheses, negative 0.1 squared. Okay. So for that one, I got 100. Okay, so I'm going to come back over here. And I'm going to need some folks to help me fill in the rest of the table. How about Sierra? What would I get if I plugged negative 0.01 into our function? 10,000? Would you guys agree? Okay. What about a negative 0.001? Peyton? What? So how many zeros do you have? Okay. Hmm. 100 million? Just a million? Okay. Does it say E to whatever? That's scientific notation. The E is the calculator's version of telling you how many places to move the decimal and in what direction.
100 after the 1.
Let me see.
Would that be 100 million? Because 6 zeros is 1.
Oh, no, you're just going to move it 8 to the right. So that would be 10.
I'm overcomplicating.
Okay. Okay, so let's see here. So 1 million. There we go. Now, here's the thing. In every other problem, we were approaching a specific value, but this one, it just looks like it's what? Yeah, as we're getting closer to x from the left, it looks like the values of y are going to get larger very, very quickly. Okay, so it stands to reason the closer I get, 0.0001, okay, if it were negative, I would get an even larger number. So what we're saying here, we're not approaching a specific number, but we're approaching infinity. And that kind of makes sense from the graph, right? If I'm approaching 0 from the left, well, the branch is going straight up along that asymptote. It's going to get infinitely close, but it's never going to touch it. So the closer you get, the infinitely higher it's going to go. Well, let's see what happens on the other side. And again, we could probably already tell from the graph. What happens if I plug in a 0.1? Yeah, so you're going to get the same thing. These are the same values. It's just one negative, one positive. And what happens when you square a negative? It's going to be positive. So this one would also be 100. This one would be 10,000. And then a million. So as we approach 0 from the right, we can tell it is also approaching infinity. So this one is kind of unique. The limit does exist. It's not approaching a specific value, but what we can say is that the limit as x approaches 0, it is approaching infinity. So it's not approaching a specific number, but we can say it's approaching infinity. Okay, questions on that? Okay. Well then, let's see here. We got some properties coming up. Let b and c be real numbers and n be a positive integer. So the limit as x approaches c of b, it just equals b. The limit of any constant is its value. Number 2, the limit as x approaches c of x is equal to c. The limit as x approaches c of x to the n equals c to the n. And 4, the limit as x approaches c of the nth root of x equals the nth root of c, which is equal to b. The limit of any constant is its value. So really a lot of what these are doing, you're just finding the limit by simply plugging in the one value of x that you're interested in. Okay, now as we've seen, sometimes there might be something going on at that location, but a lot of times direct substitution is a good way to go. Some additional properties. Let b and c be real numbers, let n be a positive integer, and let f and g be functions with the following limits. So let's say the limit as x approaches c of function f, whatever he happens to be, is L. The limit as x approaches c of function g, again, maybe they're two linear functions, maybe an exponential, quadratic, doesn't matter. Okay, we're just given these definitions. That one's going to be k. So our 5 properties here, we have a scalar multiple. So if I have the limit as x approaches c, if I'm multiplying the function by some scalar value, then that's equivalent to multiplying that value by the limit. Okay. Sum or difference. If I add or subtract the limits of f and g as x approaches c, well, then I get a sum or difference of the limits themselves. Okay. Product, if I go ahead and multiply the limit as x approaches c of f times g, it's going to be L times k, a product of the limits. Quotient is the same thing. We're just dividing. One restriction, k can't equal 0. And then the power rule. The limit as x approaches c of a function to the n power is the same as the limit to the n power. Okay. Well, let's try some examples. What's the limit as x approaches 4 of x squared? It's just going to be 16. Because what is x squared? What kind of graph is it? Yeah, it's just a quadratic. Well, there's nothing here that would indicate or tell me that there would be any kind of discontinuity or problem when x is 4. So if this is 0, 1, 2, 3, 4, okay, right here. Remember, the rule is as I approach that particular value of x from both sides, okay, hopefully we're going to find that we're approaching some corresponding y value from both sides as well. Yeah, and in this case, it's just 4 squared, which is 16. What about the limit as x approaches 4 of 5x? Yeah, 5x is just a linear function, right? Okay, it's going to go through the origin, has a slope of 5. So 5 times 4 is 20. What about the limit as x approaches 9 of the square root of x? That's just 3. Okay. Now, that's one of those cases where you would not put the plus minus in front. Anybody remember what a radical parent looks like? Looks like half of a what? Half of an exponential? Maybe if it's been flipped, but I'm thinking half of a parabola. There we go, because they are going to be inverses of each other. In fact, that would be the square root of x. Okay. All right, now this one is pretty interesting. It says the limit as x approaches pi of x times cosine of x. So I would go ahead and say, for the first time, let's go ahead and use one of the properties that we had before. I would go ahead and break it apart. The limit as x approaches pi of x times the limit as x approaches pi of cosine of x. Okay. Now, what do you think about that first one? What's the limit as x approaches pi of x? That's just going to be pi. Okay, that is pi, exactly. Very good. Pi times. Now, for this one, it really kind of depends on how familiar you are with the graph, or if you know anything kind of about the unit circle. Does anybody know what cosine looks like? I don't know if that's something that you would have done in geometry when you were talking about SOHCAHTOA. Did they show you the graphs? No? Okay. Well, this one, what I would say if you were to come across this, I might just go ahead and plug it in the calculator. The only thing is that you'll notice, like my calculator, like hopefully yours, are still in degrees. Does anybody know what's equivalent to pi radians and degrees? $180, there you go. So if I wanted to plug in, so trig right there, right next to the 7, as we've seen before. So cosine of 180. You just want to make sure you're in the right mode, because if I were to put pi in here and it's in degrees, you're going to get something that you shouldn't be getting. Okay, we're going to go ahead and push enter. There's -1. Okay, so -1. So the limit as x approaches pi of x cosine x should be -pi. Okay. Does anybody want me to show you the graph of cosine, just so you can say you've seen it? Sure. Okay. And normally I go ahead and introduce this with the unit circle. Is anybody familiar with what we call the unit circle? I know 2 young ladies for sure, but what about everybody else? If I said unit circle, would you know what I'm referring to? Okay, then I'm not going to go from that. I'm just going to go ahead and give you the graph. The horizontal axis is going to be in radians. So I'm going to go ahead and say rads. Now, the thing about cosine, it oscillates between 1 and -1. And again, this all ties back to the unit circle, why it has these restrictions. But cosine is going to start at 0. Okay, Haley, do you remember what cosine's period is? No, that's a quarter of it. So how long a period does it need in order to start repeating? It is 2 pi. So here's 2 pi right here. So that means pi is in the middle, pi over 2, 3 pi over 2. So it has its first maximum here, 0. What the heck am I doing? Yeah. 3 pi over 2. What am I doing? I think it's... Okay. Here we go, here we go, here we go, here we go, and here we go. So one period of cosine looks like a curvy V. That's how I've always explained it. So to get the entire section again, it's going to take another 2 pi radians. So it would go again, and it's going to go in both directions just over and over again. But what's really important here, you'll notice if we go ahead and take a look, the limit as x approaches pi, okay, well, as we approach pi from both sides, what do we get? We got that -1 right there. Okay. All right. Like I said, you're not going to have to worry about those graphs or anything, but who wouldn't want to know the graphs of your trig functions, right? Hey.
So, let's say I didn't remember that on my test.
Uh-huh.
I typed it into the calculator. I got positive pi. So, like, I wonder if I typed it in wrong or. Because I took the.
Wait. So did you got a +1 here?
Well, so I typed in cosine of pi.
Oh, okay.
Is that where I messed up?
Yes, because it depends on the degree you're in. See, my calculator, hopefully like yours, like I said, is in degrees. So if I were to go ahead and put in a radian measure, if I were to go ahead and say cosine of pi, get out of there. Yeah, see, it's going to give me something completely off. Okay, because the calculator, even though I know this is a radian measure, it's trying to take it as a degree measure. That's why it's giving me something so unusual. Okay. All right, but like I said, you shouldn't have to worry about that. It just a limit problem. Wouldn't worry about it. Okay. Okay, so let's see what we got here. Next up. Okay, we're going to go ahead and switch gears a little bit. We've been talking about limits for the past, 2 days. Now let's talk about how are limits related to rates of change. Now, when you see that phrase, rate of change, you immediately think what? What is it? Slope. There we go. But in IB, of course, we call it, gradient. Okay. We've already learned how to find average rates of change. In linear functions, this is known as slope. Find the average rate of change in the following graph from point A to B. Okay. So point A and B are already provided. We know A is 510, B is 2025. Well, how do I find the slope? It's been several weeks. Okay, the formula is up on the board. But what is it? Yeah, the change in y over the change in x. We call it m. Change in y over the change in x, or the difference of the y's, y2 minus y1 over x2 minus x1. Okay. So if I take the difference of the y's, and it does not matter where I go ahead and start, let's say we start with b, so 25 minus 10 over 20 minus 5. Okay. 25 minus 10 would give me 15 over 20 minus 5, 15. So it looks like my slope is 1. Okay. Now, for pretty much all the functions we're going to be looking at today, we have to refer to it as an average rate of change because as you move along the graph, the slope will not be constant. But this one here, it is, because what kind of graph do you have? It's a linear function. The slope will always be the same for any two random points that you go ahead and choose. All right, but that's not the same as if I were to have maybe a quadratic. Okay, so you have to use a tangent line in order to figure out what the slope is at a particular point. So whatever this value of x is right here, that slope is going to be pretty different from what we have right here. But we can still go ahead and find the slope of a secant line, okay, 2 points of intersection, and then just refer to it as the average, even though it's not consistent. Is everybody okay with that? Okay, and that's what this is talking about down here. Okay, so we have my formula. And remember, f of x is just referring to y, the function evaluated at a specific x value. So this is the same as y2 minus y1 over x2 minus x1. Okay. So let's see here. Let's try an example. The table shows the number of bacteria present in an enclosed environment. Find the average growth rate of the population size over the first 4 hours. Now, even though the data does not create a linear model, we can estimate the average, and that's what's important. It's not consistent as we go through, but we can find the average rate of change from 0 to 4 by using the above formula. Well, when time is 0, the number of bacteria is what? 30. 4 hours, we have 62. Okay. So it's already set it up for me. Okay. The number of bacteria for the second time, well, that would be 62. See, this is equivalent to saying y2 minus y1. Remember, when you have a horizontal table like this, the top row is considered your x's, the bottom row is considered your y's. Okay, so this would be 62 minus what? 30. The value of the function at the first time. And then I'm going to divide it by the difference of the time. So 4 minus 0. So basically, we have these ordered pairs, 0, 30, and 4, 62, that we're finding the average rate of change of. Okay, the average slope. So let's see, what is 30? I almost said it. 62 minus 30, 32, divided by 4 is 8. Okay, so we can say on average, you're getting about 8 bacteria per hour. Okay. But if you go ahead and take a look at the table here, we can see that's not going to happen. How far is it between when it started to 1? That's 6, and 36 to 43. Okay, 43 to 52, 9, 10. So you'll notice it's not consistent, but we took the average. So maybe a little more, maybe a little less, but it's about 8 bacteria per hour. Is everybody okay with that? Okay, that's the average rate of change. So here we go. The average rate of change between 2 points on a graph can be found by finding the slope of a secant line between the 2 points. Okay, if we have 2 points on a graph, P x f of x, and point Q x plus h f of x plus h, a point h units to the right of x, we can find the slope of a secant line passing between them. Okay, so I'm going to go ahead and recreate this graph, because when we really get into it, that guy right there, he's going to be super important to us in the next lesson. He's what we refer to as the difference quotient. Okay, the difference quotient is the universal method of finding the derivative of a function. Okay, but I'm getting a little ahead of myself. How do we get this in the first place? Okay, I'm glad you asked. Okay. All right, I'll say here. So let's say we have some kind of function f, and it's going to curve maybe like this. Okay, and we have a line that just goes straight through it. Okay. Now, if a line intersects another graph in 2 points, we call it a secant line. Okay, 2 points of intersection. If it only crosses in 1 point of intersection, you know what we call it? We call it a tangent line. Okay, very useful with circles. So let's say this point right here. Okay. Well, some value of x is going to give me this corresponding value of y in the function, right? But what do we like to use instead of y? What's that notation? F of x. So this function here, we're just going to call him f, so that this point is x, f of x. Okay. Whatever that is, the function is taking x and it's going to spit out some y value. Well, let's go ahead and say that down the road we have some other value where the other point of intersection is going to be. But let's say that the distance between them is h. Okay, so what would you actually say this value of x would be that I'm going to plug into the function?
X plus h.
Yeah, whatever the distance is, just add it to the original value. So if x plus h represents the input for the second point, what would represent the output? There you go. See, I'm taking x plus h and I'm plugging it into the function. So that's where we're able to get those points in your diagram. X, f of x plus h. Okay. Is everybody okay with how I got those ordered pairs? All right. Remember, f of x plus h, they just represent y values. But now let's go ahead and find the slope. I'm going to start from here. The difference of the y's, f of x plus h minus f of x over. Now I'm going to take what? Oh, I'm sorry, I forgot the plus h right here. Okay. The x plus h minus x. And what do you notice is going to happen in the denominator? The x's cancel. Okay. So a derivative is a very, very powerful strategy. It's a very useful tool in calculus, but it's based on the most simple idea in algebra. It's just slope. Yes?
So with that, you're just finding the distance between.
Yes. Now, what we're going to start doing later, because in the next lesson, we're going to go ahead and take expressions and we're going to apply it to this formula. But what we're going to do in order to find the derivative, and again, I'm getting a little ahead of myself, you have to take the limit as h approaches 0. I want to take the secant line and make it a tangent line. So kind of imagine that this graph was tangible. I could actually grab it with my hands. If I grab this point right here and I started to slide it along the function towards the other point, well, what's going to happen to the distance between those values? It's going to get smaller, or as we say, it's going to approach 0. Now, there's going to reach a point where those two are going to merge. The 2 points become 1, so we no longer have a secant line. We have a tangent line. And the slope of a tangent line at a specific value of x, that's what the derivative will give you. Eli, you okay? No, it's okay. It's okay. Like I said, I'm getting a little ahead of myself because calculus is fun. Just ask the 2 young women who already went through it. See, Haley's shaking her head like, man, it's the best fun I ever had. Okay. Okay. All right. Okay, so before we really start getting into derivatives, let's go back to just average rate of change. Okay, let's do some more examples. So here we go. Let f of x equal the square root of x squared minus 9. Find the average rate of change from x equals 3 to x equals 6. Okay. Well, they're giving you the values of x, but in order to find the average rate of change, I need to know the corresponding y values that go along with them. Okay, so maybe we can just go ahead and create a table here. Let's say x, f of x. The 2 values of x they're giving me are 3 and 6, right? Well, how in the world am I going to figure out the y value for 3? Plug it in. There you go. So f of 3 would equal, this is the square root of, instead of x squared, I'm going to say 3 squared minus 9. So that's the square root of 0, but what's the square root of 0? 0. Okay, so we have one ordered pair 3, 0. Okay, now I'm going to do the same thing for 6. So f of 6 is equal to the square root of 6 squared minus 9. So that's going to give me 36 minus 9. Okay, so that's going to be square root of 27. Okay. Now you'll notice they've already provided those here. See, they got the 3, 0 that we got, but they're showing 3 square root of 3. How'd they get that? There you go. See, we didn't choose to go decimal in this one, so we can still simplify it. We're looking for the largest perfect square that'll evenly divide it. In this case, 27 can be rewritten as 9 times 3. See, I can take the square root of 9, so I can pull that out, but if I take the square root of 3, I'm going to get a decimal. And we don't want that. We want to stick with the radical, because it certainly lives up to its name. Really? It's radical. Because y'all still talk that way, right?
Yes.
Yes. So I'll go home and tell Bay that tonight. My speak is on fleek. There you go. Oh my God. It's a wonder that, so many people in here, your eyes aren't so tired all the time from just the constant rolling every time I say something. It's like, oh God, here goes Mr. West again. Okay. Okay. All right. So is everybody okay with how I got my ordered pairs? Okay. So now let's go ahead and find that slope. Okay. So the difference of the y's, 3 square root of 3 minus what? 0 over 6 minus 3. And remember, when you're finding the slope, it doesn't matter in what direction you go. We can even go in the other direction if you guys want, because those negatives are going to cancel. So we're going to end up with 3 square root of 3 over 3. So I would say the average rate of change is just the square root of 3. And remember, that's average, because this guy here, he is not a linear function. He's a what?
Call him a curvy boy.
All right. Let's try this one. Okay. The concentration of a drug in milligrams per milliliter in a patient's bloodstream T hours after an injection is approximately modeled by the function. Okay, so what it's saying here, this is just another notation. You have some value that you start with and you apply it to this function. So it's like you're saying have T, and this right here would be f of T, if it kind of helps you to think about it in that way. Okay. Of course, T has got to be greater than or equal to 0, because T is representing what? Time. Yeah, and it doesn't make sense if we were to say time is negative, then that means it reverses itself, and that's not the way, we understand it. Okay, so find the average rate of change in the concentration of the drug present in a patient's bloodstream during the first hour, the first 2 hours, and then during the second and fourth hour. Okay, so why don't we go ahead and start here. Let's create a table. So this is going to be T. I'm going to go ahead and call this f of T. Now, how far should we go? 4. So I'd go ahead and say 0, 1, 2, 3, 4. Okay. So let me give you about a minute or two. Let's take each one of these, 0 through 4, one at a time. Let's plug them into this function. And let's go ahead and get the corresponding values. But let's leave them as fractions. Okay. Because how do you put the fun back in function? You work with fractions. See, Spencer is shaking his head like he knows what I'm talking about. Huh?
What about decimals?
What about decimals? Well, they have a point too, but fractions are going to be better. On a completely different topic, did anybody happen to notice that the first Joker trailer was dropped?
It looks different.
It looks pretty good.
I think it's gonna be good.
I think it's going to be very violent because I don't think they're showing a lot of stuff yet, but
Yeah, they haven't shown
we can hope.
anything watchable, like, where's all like the criminal Joker stuff?
Well, remember, this is more of an origin story, and they're taking a lot of influence from The Killing Joke, but it looks like they're trying to make this more realistic. Not that he's going to be dropped into a vat of chemicals, that he's a man who's basically got some mental health issues and basically finds his confidence, finds his voice when he wears his clown makeup. Oh God, I can't wait. Anyways, go ahead, I'll let you do math. And I think we're almost done. I think after this we have, yeah, we got this right here. Very good, very good. Okay. Excuse me. Everybody about ready? Or do we need another few seconds? Okay. What should I get if I plug in 0? 0. 1. Okay, that would be what? 2 nights. Okay, thought I heard something else. All right, then 2. Okay, sorry, one more time. 1/4. 3. 6 35ths. Oh, I'm sorry. And what should we be getting for 4 hours? 1 night. Okay, does anybody want me to go back and plug in a corresponding value to see how we got that ratio? No? Pretty good. Did everybody get those values? Okay. Well, let's take a look at A. All right, well, it says find the average rate of change during the first hour. Okay, well, with the first hour, okay, we're talking about these ordered pairs right here. So 0, 0, and 1, 2 9s. Okay, so the average rate of change, I'm going to be looking at 2 9s minus 0 over the 1 minus 0. Well, what's the average rate of change? Should end up being 2 9s. Okay. Now, B, it says during the first 2 hours. So I'm going to go ahead and use a different color here. So during the first 2 hours, okay, just to kind of color code it so we have that. All right, so what would be the numerator? What terms or values would I subtract in the numerator? 1/4 minus what? Ooh, 0. And then I'm going to divide that by 2 minus 0. So it looks like I have 1/4 divided by 2. That would end up being 1/8. A couple different ways you could do that, or I'll even just, does anybody want me to talk about how we got the 1/8? Or does everybody feel pretty confident? Okay, then we'll leave it as is. And what was C during the second and fourth hour after the drug was administered? Okay, so I'm going to go ahead and get another color here. Let's go purple. So this time we're going second and fourth. All right. So I would say we're going to go ahead and stop here today after we take care of C. Would anybody like to come on up and show me what and how they got? So many hands. I just need one. Spencer? Okay. Thank you very much. So 1 9 minus 1/4. 4 minus 2. Straight to it. Negative 570 seconds. That's the average rate of change between the second and fourth hour. Okay, very good. How many people got that right? Okay, so a few hands. Does anybody want me to kind of elaborate on what he did to show you where we got the values? Okay, well, let's start with the fractions. We got to take 1 9 minus 1/4. So we need a common denominator. So what's the first value that both 9 and 4 will divide into? Well, now 4 will go into 12, but 9 won't. So 36. So I'm going to multiply this by 9 over 9, 4 over 4. So this is 4/36 minus 9/36. See, these are your equivalent fractions. And that's where he was able to get the negative 5/36. Okay. But dividing it by 2, he just took the negative 5/36. That's equivalent to multiplying it by 1/2. And that's where he ended up with the negative 570 seconds. Good. Okay. How are we doing? Any questions? All right, we'll go ahead and wrap this up tomorrow, and we should be able to go ahead and begin derivatives. Okay.